Hello, today I'll be showing you guys how to do problem 3.11 in Griffith's Introduction to Electrodynamics. Now 3.11 reads, right here, two semi-infinite grounded conducting planes meet at right angles. In the region between them, there is a point charge Q, situated as shown in figure 3.15. Set up the image configuration and calculate the potential in this region. What charges do you need and where should they be located? What is the force on Q? How much work did it take to bring Q in from infinity? And suppose the planes met at some angle other than 90 degrees. Would you still be able to solve the problem by method's images? If not, for what particular angles does the method work? This is figure 3.15 right here. Now this problem is really good to practice your separation vectors and some core theories of, or core ideas of methods of images. So I'm going to move this out the way. Hi, so I had an error in my original video. This is a correction to that video. So in the video I mentioned that all our point charges for method's images add up to 0. That is not true. The image charges for method's images are placed in such a way to meet the boundary conditions across our conducting plates. So we have our point charge here, so our image, right, we're going to be placed here, a negative Q here. So the potential from this charge and this charge add up to 0 across this plate, right? And then there's another plate here that will place another image charge here, so the potential across the vertical plate here is 0. And then this image charge is also going to contribute, or is going to affect this horizontal plate, so we need to place another point charge here of positive Q, right? So then the potential from this negative Q and this positive is going to cancel out across this horizontal and keep the potential at 0. And this positive Q is also going to be the same one used for this negative Q here. Right, so that is how we place the point charges from these images, so the potential across the plates are equal to 0. The first part of the problem is to find the potential in this region up here, which I'm going to label as X, Y, Z. Alright. Alright, so we know the equation for the potential between many points is going to be as follows. 1 over 4 pi epsilon naught times the summation of all the points, all the point charges, which is 1 of the charge over the separation vector. Okay, so the first step is to find what our separation vectors are from this point, and I'm going to label these points as 1, 2, 3, and 4. So our first separation vector is going to be from here to here, and our second one is going to be from here to there. Sorry, all these lines are going to be overlapping each other, but and then the third one is going to be diagonally across, and the fourth one is going to be from here to there. Okay, so now we know the separation vector is defined as the field point minus the source point, and our field point is going to be x, y, z, and our source point is going to be wherever our point charge is. So our first one, the field point x, y, z, and our point charge is located at positive A and positive B. So A, B, and we have nothing in our z-axis. It's going to be 0. So that means we're going to have x minus A in our x-hat direction plus y minus B in our y-hat direction plus z hat. Okay, that is our first separation vector, and then we need to get our magnitudes since the potential depends on the magnitude of the separation. So this is going to be the square root of all these terms squared. Okay. And then the rest of the separation vector is going to be following this same sort of format, except our charge is going to be at different locations. So our second one is going to be at negative A, positive B. So that's going to give us x plus A in our x hat direction, plus y minus B in our y hat, and our z stays the same. And the magnitude again is going to be the sum of the squares, square root. Okay. Now for our third one over here, which is located at negative A, negative B. This is going to give us x plus A, x hat plus y plus B, y hat plus z, z hat. And then this magnitude is going to be the square root of x plus A squared plus y plus B squared plus z squared. And then finally, our fourth one is going to be x minus A x hat plus y plus B y hat plus z z hat. Magnitude again okay, so now we have all of our separation vectors written out. Now we can plug our magnitudes into the potential function. So 1 over 4 pi epsilon naught times our first point magnitude, which is that one. Well, I'm just gonna write as script R for now, because we can take out the Q later. So our first point is positive Q over script R 1 magnitude plus our negative Q over the script R2 magnitude plus the positive Q of the third one plus the negative Q of our fourth one. Okay, so we take all these Q's out. Q over 4 pi epsilon naught times 1 over our first magnitude, which I forgot to label. So it's going to be 1 over the square root of x minus A squared plus y minus B squared plus z squared. Okay, and then minus 1 over our second, which is, forgot to label again, x plus A squared plus y minus B squared plus z squared. Okay, plus our third one, which is over here. Okay, and then I have to write our fourth one down here, which is that one over there. Which is the potential in this region up here. Okay, so now for our next part is the force onto Q. Okay. And we know the equation for force between two point charges to be as follows. So the first point charge over 4 pi epsilon naught times the summation of all the other charges. So I'll explain it later, but this is going to be from 4 to I equals 2 of the charge that we're considering over our separation vector magnitude squared times the unit vector of our script r. Okay, and then since we have everything in terms of, so I'm gonna be, for our separation vectors, instead of writing whole new ones to find the separation between our point charge here and here, I'm gonna be reusing these, but evaluate them at where our point charge is here, which is A, B, 0. So that's why I wrote we have summing up to 4 and starting at 2, because we have our separation vector 2, which is our point charge here, and our field point basically is going to be, instead of x, y, z, is going to be a, b, 0. And since we have everything in terms of the vector and the magnitude, I am going to rewrite this as q over 4 pi epsilon naught 4 2 of our charge cubed vector I. Okay, so we still need to rewrite our forces a little bit, but it should be a little bit quicker. So basically we'll be writing our script R2 at A, B, 0 at our first point charge, which is going to be 2ax hat. So we go back here. So if we plug in A for x, it's going to be 2ax hat. If we plug in B for y, it's going to be 0y hat, and then 0z hat. Okay, and then that makes our magnitude super easy. It's going to be 2a. And then for our third one, we plug in a, b, 0. We are going to get 2a x hat plus 2b y hat. And then the magnitude is going to be the square root of all those squared. And then bring the 4 out to a squared plus b squared. Alright, and then our fourth one, evaluated at a, b, 0, is going to give us 2b y hat, and then the magnitude is going to be 2b. So now we can plug all these into our force equation up here. So the force at x, y, in terms of x, y, z, is going to be equal to q over 4 pi epsilon naught times the first, or our second point charge, which is a negative q, over the second script r magnitude cubed, so 2a cubed times the vector, so 2a x hat. Right, and then we do our third one, which is going to be a positive q over over our 2 square root a squared plus b squared cubed over, or times 2a x hat plus 2b y hat, and then plus our fourth one, which is a negative q point charge over 2b cubed times 2b y hat. Okay, so this 2b we cancel out with one of these, make that squared. Same thing over here. And then I'm going to take out the q's, bring it onto the outside. So we have q squared over 4 pi epsilon naught times negative 1 over 4a squared plus, and then I'm going to distribute this out into the x hat and y hats. So we're going to have 2a x hat over 2 cubed, which is 8, times our a squared plus b squared to the power of 3 over 2 plus 2b y hat over 8 a squared plus b squared power of 3 over 2 plus negative 1 over 4b squared y hat. Okay, so these 2's will cancel out, bring this down to a 4, and then we can take out a 4 here, make that 16. 16 pi epsilon naught, and then, oh sorry, I forgot the x hat here. Okay, and then so we will combine these terms, so we'll have a over a squared plus b squared power of 3 over 2 minus 1 over a squared times x hat plus b over a squared plus b squared power of 3 over 2 minus 1 over b squared in our y hat direction. And that is our force onto charge Q due to all the image charges. Okay, so now the next part is to calculate the work coming in from infinity. Now, the equation to calculate work from point charges coming in from infinity work so the equation that we need is, or the equation to bring in a point charge in from infinity is going to be the charge over 4 pi epsilon naught, and we have to account for all the charges, so we're going to sum up all the other charges over the magnitude. Alright, but this is without considering conducting plane. Earlier in the section, it tells us that the work due to images from a conducting plane is actually going to be 1/2. This is because on the other side of our conducting plane, the electric field is 0, so the work to bring in a point charge is going to be 1/2 of what it would be if the conducting plane wasn't there. So I will times this by 1/2. So that will give us Q over 8 pi epsilon naught times the summation of our charge over the separation, which is going to be using the same ones that we derived from the we calculate the force onto Q. So our second charge is going to be negative Q And our second separation magnitude vector is going to be 2a. Our third one is a positive q times 2 times the square root of a squared plus b squared, plus our third one, which is negative q over 2b. And then we can bring out these q's, q squared, and then bring out these 2's, so make that 16. And then we have negative 1 over a minus 1 over b plus 1 over a squared plus b squared. The last part of the problem is, suppose the planes bend at some angle other than 90 degrees. Would you still be able to solve the problem by the method of images? If not, for what particular angles does the method of images work? Alright, so let's first see by what we know works. We just proved that it works for a 90-degree angle between our plates. Alright, we have a q here, a negative q here, and then our positive here. Alright, so we just proved that it works. That it works for 90 degrees. Alright, we know that it works for 80 degrees or 180 degrees because that's just a regular plane. Alright, so we have, if we had a q here, it is gonna make an image here. We know it works for that. And then we see that we go from 180 to 90. Well, the next step down would be 45. Alright, so we do another xy plane here. And then I'll draw our conducting planes in red. Alright, so this is for a 45-degree angle, and we'll place our point charge here, so it reflects across the horizontal to here, and this one also reflects across the one at an angle to here. Alright, and then to make drawing it easier, we're gonna draw another 45 here, but this is not a conducting plane. This is just to make it easier to draw where the points are. I will explain how this all works out in a second, but this negative q is going to get transferred to over here, or it's going to make a positive q from here. You can also view it as this negative point charge here is going to get reflected across the horizontal plane here, down to here. And then this positive q is we're basically going to reflect everything across the y-axis over. Right, so we're going to have a negative q here, and then it will reflect across the plane on the angle here. And then we will go across the horizontal plane, make a negative q here, and then we need to place our last one here of q, which is also going to be attached to it. So this placement of images works because our point charges, the potential from them all add up to 0 at the boundaries. Alright, so again, our boundaries are our potential is 0 across this plate and then across this plate. And we can verify this by, if we look at the one at an angle here, we have this negative q and this positive q, this positive q and this negative q, this positive q and this negative q, and this negative q and this positive q. So they all cancel out with each other because they're all the same distance away from the angle. And the same thing for the horizontal. We have this one and this one, this one, this one, this one, this one, this one, this one. Those all add up to, the potentials from them all add up to 0 once we reach the plate. So what's going on here is we have 180, 90, and 45. This will also work for 60, similar placement to these. And what is happening is it's going to be integer divisors of 180, right? So 180 divided by n, where n is in integer. Alright, so 180 divided by 2 is 90, divided by 3 is going to be 60, divided by 4 is 45, and so on. And so we know that this image is going to work for this condition. Let's see what happens when we go outside this condition. So we do an angle that is not a integer divisor of 180. So we'll do another XY plane here, and then we'll have a connecting plane along the horizontal, and then we'll have another one, say at this angle. So this is not a divisor of 180. Alright, so then we will place a charge here. This charge is going to get reflected across here to make a negative Q. Alright, so potential 0 across the horizontal. And then this one's also going to get reflected across the one at an angle, but it's going to go sort of all the way like over here. Alright, but now we need to reflect it across the horizontal, so that's going to get reflected back up into over here. But now this is where we run into a problem, because now we placed an image charge outside of our conducting planes area, right? Because everything in like this area up here cannot contain a image charge, which invalidates Method's images. So this means that angles that aren't divisors of 180 would not work, and because you will end up placing a image charge outside of a valid region. Alright, so that is our answer. Integer divisors of 180 degrees is a valid angle to be able to use Method's images.